Arun, sir?
Yes, sir.
Yes, sir, we can start, sir.
Okay, well. Good evening to one and all. It's a happy occasion to have you all for the webinar 97th in series, a weekly online lecture, Engineers Talk, being organized by Institution of Engineers India, Salem Local Center, in commemoration of its 30th anniversary celebrations. I would like to request the chairman, IEI Salem Local Center, to welcome the guests and the gathering. Please, sir.
Yes, sir. Thank you, sir. Am I audible, sir?
Yes, sir. Yes.
Yes, sir. Good evening to all present for today's session. On behalf of the Institution of Engineers India Salem Local Center, I extend my warm greetings and a hearty welcome to this 97th special webinar under our weekly online lecture series, Engineers Talk. At the outset, I wish to recall the pride that our IES Salem Local Center is celebrating its 30th anniversary this year. Over these three decades, the center has been actively engaging professionals, academicians, researchers, and students through technical talks like this, seminars, workshops, and industry academia interactions. This engineering talk series, which is nearing its 100th week, stands as a testimony to our commitment to continuous learning and knowledge sharing. We are indeed honored to have with us today Dr. Satya S. Sensor, Assistant Professor, School of Computer Applications, KIIT, Odisha, as our chief guest and keynote speaker. Sir, we extend our heartfelt gratitude for accepting our invitation amidst your busy academic schedule. We look forward to your insightful lecture on smart fluids, how AI is reshaping fluid mechanics. The fusion of artificial intelligence with fluid mechanics is a fascinating frontier, and your address will certainly enlighten and inspire our members and participants. I also take this opportunity to welcome our esteemed members of IEA, respected council members, respected committee members, professionals from various disciplines, faculty colleagues, dear students, and our honorary secretary, IEA Local Center committee members, engineer talk team members, especially Arumugam sir, and our IEI staff engineer T. Thiagu, who have joined us virtually this evening, and they are the real motivators and heroes for making these again season into 100th event. Your continued participation and encouragement make this initiative meaningful and successful. Before we move forward, I humbly acknowledge the constant again support and guidance from our IE headquarters, Tamil Nadu State Center, our past chairmen, past secretaries, and also all well-wishers who have been instrumental in the growth of IES Salem Local Center. And we are exactly in the 32nd year only because of their support and hard work. With these words of welcome, I once again invite you all to be part of this intellectually enriching session. Let us listen, learn, and get inspired. Thank you.
Thank you, sir, for your welcoming. And now it's my pleasure to introduce the chief guest and the keynote speaker, Dr. Satya S. Sen, Assistant Professor in the School of Computer Applications, Kalinga Institute of Industrial Technology, Bhubaneswar, India. His research interests include computational fluid dynamics, heat and mass transfer, hybrid nanofluid, flow over stretching surface, flow over a cylinder, etc. He has used different advanced environments like MATLAB, Mathematica, LaTeX, etc. for his research. He has published research articles in various SCA Scopus indexed journals like International Communications in Heat and Mass Transfer, Physica Scripta, Heat Transfer, etc. With these words of introduction, I would like to invite Dr. Satya S. Sen to present on the topic Smart Fluids, how AI is reshaping fluid mechanics. Please, sir.
Thank you, sir. Is it visible, sir?
Yes, sir. Yes, it is visible.
Okay. So, very good evening to one and all present here. First of all, I'd like to thank the organizers for giving me an opportunity to speak on the topic. The topic of today is smart fluids and how AI is reshaping fluid mechanics. Now, we all know that slowly AI is growing, right? And it is extending its feathers to different fields where a lot of applications are there. So, like that, in fluid mechanics, slowly AI is having major impact while finding different results. So before we go to the application part of AI, we have to first understand what is this fluid mechanics and what actually we do in fluid mechanics. Then only we can actually understand how this AI is helping, and then we'll go to the smart fluid thing, right? So first of all, what is this fluid mechanics? So fluid mechanics is a branch of physics that studies the behavior of fluids at rest or in motion. Now, in general, what happens when we talk about fluids, people tend to think that fluid means liquid. But actually, it is not the case. Fluid means it can be liquid, it can be gases, it can be plasmas, like air. Air is also a fluid, right? So, in fluid mechanics, what we do is we try to study the behavior of the fluid when it is at rest or at motion. And by behavior, we means what? When suppose some forces are acting on them. So, how that fluid is going to behave, right? So, that is what we are going to cover in fluid mechanics. Now, in general, we use the term computational fluid dynamics, right? Now, as I already told you, before going to that, this fluid mechanics is actually divided into two parts. When we talk about fluid, it can be two things. Either it is at rest or it is at motion. So when the fluid is at rest, we say it is fluid static. But when the fluid is at motion, we say it is fluid dynamics. Now, as you all know, in our practical application or day-to-day life, it's almost every case that fluid is in motion, right? So fluid dynamics becomes an important aspect in nowadays scenarios. So to understand the fluid dynamics, we need to somehow know the basic concepts of computational fluid dynamics. Now, what happens is what when we talk about fluid dynamics, we have to model some mathematical equations to understand how the fluid is behaving in fluid dynamic case. Now, it is not always possible for us to actually solve these equations exactly. And by exactly, I mean what? Like suppose there is a differential equation given, like dy by dx equal to x. Now we can solve those small kind of or linear kind of differential equations. But when we are going to take practical applications, like in fluid dynamics, suppose like in the picture you can see a bird is flying, right? Now that flight motion can also be modeled using mathematics, but it is going to be highly nonlinear. So those nonlinear cases, it is very difficult to find, and sometimes it is almost impossible to find the exact solution. So for that, what we need is we have to find an approximate solution. And for approximation, we will use the concepts of numerical analysis. So this computational fluid dynamics is just the case that when we apply numerical analysis in fluid dynamics, we say it is computational fluid dynamics. We are using computers to calculate the required solutions. Now, as I said, fluid dynamics is a very important aspect of our life. Why fluid dynamics? You see, right from the beginning, like when you are giving water to your plants in your garden, or you are taking a flight, or in your own body, when where there is blood and blood is flowing, everywhere fluid is there, and everywhere it is in motion. So fluid dynamics becomes a very important aspect. And in order to understand these aspects, we have to understand the concepts of fluid dynamics. Now, when we discuss about fluid dynamics, we basically divide this fluid dynamics or these fluids into two types. One is a Newtonian fluid and one is a non-Newtonian fluid. Now, in Newtonian fluid, what happens? Now, how we categorize is there is a law called as Newton's laws of viscosity. Now, depending on the nature of this viscosity, we divide this fluid into two types, Newtonian and non-Newtonian. Now, somebody might ask, what is this viscosity? Now, simply I can tell viscosity is kind of a resistance that is applied by the fluid itself. Now, for example, suppose I am telling that I will spill some water on a table. Now, that water is going to move on the table, but after some time, it is going to come to a rest. Now, how that water is actually stopping? Now, somebody might say that the table, the surface is giving that resistance. That is true. But there is a concept called as viscosity where the particles that are within the fluid, they also resist the flow. And that nature is called as viscosity. So what happens is, sometimes if we give the force, some external force is given to a fluid, that nature, that viscosity changes. So wherever the viscosity changes, we say it is a non-Newtonian fluid. Where the viscosity does not change, we say it is a Newtonian fluid. Like for example, I will show you one example also here. Just I'm taking a case. Suppose I spill water on a table and the water is moving. And suppose I am forcing it from above in the perpendicular direction. And by forcing, I'm not telling that I'm keeping an obstacle before it. I'm just putting a force. You see, if the water was tend to start from A and stop at B, even after you apply the force, it's still going to move from A to B. It's not going to stop. But there are certain fluids, if you apply that perpendicular force on them, if they were supposed to stop at B, they might stop before, they might stop after. That means what? That the resistance that is existing within that fluid, it is changing. That means that viscosity is changing. So those kind of fluids where that viscosity is changing are called as non-Newtonian fluid. And why it is important? Because our own body is made up of non-Newtonian fluid, that is blood. Okay. So I'm just showing you a simple example I've taken from the internet. You see in this picture, when you are actually moving your finger slowly in the fluid, you are able to easily move the fluid. There is no problem. But once you try to punch it, with hard force, it kinds of resist your punch. That means what? Its viscosity is changing when you're giving the force. So it is behaving like it is a hard material, right? And that is what non-Newtonian fluid is all about. Suppose in this case, if you would have taken water, you could have easily punched your fist, inside the water, but not in this case, right? So this is an example of how non-Newtonian fluids behave in real life. Now, similarly, when we talk about fluids, we should know that there are two kinds of flow in fluid. One is laminar flow and one is turbulent flow. Now, when we say laminar flow, it means what? Suppose my fluid is moving, right? Now, there are various layers inside the fluid. If those layers are parallel to each other, that kind of flow is called as a laminar flow, or in general, we say it's a smooth flow. But in case of turbulent, that layers are not parallel to each other. They're kind of mixed and zigzag in nature. Now, in general, turbulent flow is what we find everywhere, right? So it becomes very important for us. Now, for a small example, if I want to take, you see this picture you can see. In the left side, you see there is a laminar flow. You see how smooth the flow is. Until unless you abstract it with your finger or with any force, it's going to flow like that. So smooth. It's like it's not even moving, right? But in the left side, you see there is an example of a turbulent flow. It's like we all have your this dhoop sticks in our home, right? And when we actually light the dhoop stick, you see, initially the air or the smoke that is coming out, it will be very smooth in nature. But once it goes to a certain level, it kind of becomes, zigzag in nature. And then again, it becomes dispersed. So that dispersed thing is called as turbulent flow. And it's in the picture, you can see how it is transitioning from a laminar flow to a turbulent flow, right? So it becomes very important aspect of yours. Now, what is MSD? See, I have taken different parts of fluid, right? Because we are going to talk about smart fluids. So we have to understand what are the basics of fluid, right? That's why I talked about your Newtonian, not Newtonian, and I talked about your laminar flow or turbulent flow. Now MSD. Now what is this MSD is, there are certain fluids whose nature can be changed by applying external force, such as magnets or electric fields. Right. So such kind of fluids, when we take and we study about them, that comes under magnetic hydrodynamics. Now, when we talk about smart fluids, we are talking about smart fluids. It itself says that the fluid is smart. That means it can change its nature. It can behave according to you. It is smart enough. So in order to understand those kind of fluids, we need the concepts of chemistry. Now, it was first initiated by Professor Hans Alvin, for which he also got a Nobel Prize, right? And there are certain examples of your smart fluids like your electrolytes or salt water, plasma, etc. All are there. So now, what are the applications of MSD? You see, when we take our own Earth, we all know this our own Earth is it's kinds of like a act like a magnet, right? We have a North Pole, we have a South Pole, and within our Earth, there is a lot of fluid in core, like in form of lava or other things. So when that lava also moves, that lava is actually kind of a electromagnetic field on, means your smart field on it, not exactly, but that actually reacts with a magnetic field. So when this that fluid moves, the Earth magnetic field is also affected. So to study those natures, to study how it is behaving, we need the concepts of MSD. Then again, there is a very uprising topic called as magnetic targeting. Now, what happens generally is, if we take a case of tumors or cancers, suppose there is a cancer or a tumor in my body, in our body, and it's at a very deep place, right? So what we generally do nowadays is we do chemotherapy. That's available, right? So in chemo, what happens? We deliver the drug to the spot, the tumor spot, and it kills the bad tissues. But what happens is it kills the bad tissues, that is okay, but it also kills the surrounding good tissues. That's why a lot of side effects you are able to see, like hair fall or degradation of health, and sometimes it might be life-threatening also. So by using this magnetic drug targeting, what we are going to do is we are going to send the medicine using a fluid particle. So what we'll do is we'll put the medicine inside a fluid block, you can say, and that fluid block or that particle will be affected by the magnet. That magnet, you can keep it external also. So what will happen is that now we can actually deliver the fluid, deliver the medicine directly to the spot where the tumor is happening. So like this, what will happen? We will reduce the side effects that are going to cause. Right. So it is a very emerging site, and a lot of work has been going on in magnetic targeting, and it's a very interesting part. Then there is astrophysics also. Astrophysics means when we talk about your solar flames are actually a very good example of these electrofluids or which are actually affected by the magnetic field of sun and earth also. Right. Now, next concept that we should actually know is heat and heat transfer. Now, we have studied in our school days that heat transfer takes place by three methods, that is conduction, convection, and radiation. Now, conduction means what? If you hold a solid and you throw it into a heat source, the heat is going to get transferred from particle to particle, right? That is called as conduction, where the heat is transferring with the help of particles. When the heat is transferred with the help of a fluid, we say it is convection. And when it is using electromagnetic waves, we say it is radiation. Some basic concepts, right? So in fluid dynamics, we will mainly be using convection because we are going to do that heat transfer, which will go to the coming later part. We are going to use convection mainly, right? And these are some of basic examples of heat and mass transfer where both are taking place. You can see as Earth atmosphere is already good example where the water evaporates, goes up, forms cloud, again comes down. So all kind of heat and mass transfer are actually taking place. Now, why I'm telling all this? Because we are going to talk about smart fluids. See, in general, the smart fluids are not present. We have to make them. So suppose there is a fluid present, normal fluid, may be water or oil, something. What we are going to do is we are going to add nanoparticles. We are going to add nanoparticles that actually get affected by the electric field or the magnetic field. So those kind of fluids are called as nanofluids. And those we are referring to here as smart fluids. Right. And when we add nanoparticles to the fluid, you see we're adding particles, so those particles are also moving. So kind of mass transfer is taking place. And obviously they are transferring the heat. So heat transfer is also taking place. Now, coming to my area, actually, my main area is we to work on how to cool different surfaces in large scale industries. See, in large scale industries, what happens? There are a lot of big machines, right? They work 24/7 continuously. May it be production unit, may it be a service unit, whatever. So those devices, they need to be maintained, at a particular temperature. Otherwise, what happens? Their longevity will reduce, and it will be a very big loss. So in order to actually cool down those kind of systems, we use these smart fluids. So what we do here is we are going to take nanofluids and we are going to flow those fluids over those surfaces. And what these nanofluids will do is they will extract heat from the surface and they will release the heat outside. Outside, or you might also use those heat, in different conditions, like you can use a heat exchanger, you can use those heat. Also, there are different applications are there. But our main objective is we have to cool down those uh, surfaces, right? So there, what will happen is nanoparticles or nanofluids we are using. Now, different type of nanofluids have evolved. When we add one nanofluid, when we add one particle, we say it's a nanofluid. When we add two particles, it is said a hybrid nanofluid. Then ternary is there. Then penta has come. A lot of things are being developed, right? Depending on the number of nanoparticles you are adding. So I will not go to that part. That's the application part. But the main thing is, these smart fluids are actually helping us in this way, that because they are able to react to magnetic field, react to electric field, now we can actually control the fluids according to our wish. How it should flow, when it should be slow, when it should be fast. Those kind of things we can do here, right? So this is a small example that I have taken. You see the practicals were actually, different directions. But once you apply a field to it, maybe magnetic, maybe electric, it kinds of behave in a linear way, right? So this is what we actually require here. This is how the smart fluid help in my case, generally. Right. And there are a lot of applications out there. Like I will show you now. Right. So you see, this is again one more smart fluid that we have taken here. And you see, there's a magnet above, right? And it is slowly getting attracted towards the magnet. See how slowly it is going to behave. So what happens is here, sometimes in your vehicles, or maybe other stuff also, you are using gears or you are using brakes, right? So there, if we use this kind of fluid, it is going to help us improve their performance. How? You see, when we take a smart fluid, you see how we can actually mold it to the given frame that is given to us using external field. Like this, it is going to help us. Now, what is the application here? Why we need to mold it according to the gear present or the brakes that are present here? You see, there is two kind of vehicles you can see. One that have MR fluid shocks and one that have standard shocks. So you can see how bumpy that ride is, in the standard shock. But when you take the MR fluid, see how much it is reduced. That means what? That fluid is focused on the point where it can reduce that effect, that impact. So how we are doing is we are actually directing that fluid towards that particular surface. That's why it is helping us to actually absorb more impact, and it is actually becoming more smooth. And this kind of technologies are already present here. Right. So these are certain applications that I told about what is a smart fluid and everything. Now, I have been telling you one thing, that this fluid dynamics, we are going to use mathematical models. We have seen how the applications are, right? But how to understand these applications? So, in order to understand that, we need to develop mathematical models. Now, generally, what happens is we develop mathematical models using nonlinear differential equations. It can be linear, but because I'm talking about practical applications, so it will be mainly nonlinear. That's why I told you computational fluid dynamics. So this is actually the frame of a fluid dynamics, general frame of a fluid dynamics problem, right? So here you can see a name called as Navier-Stokes equation. So this whole set of equation is called as a Navier-Stokes equation. It actually, basically, it might look complicated, but actually it is very simple. It works on three laws. Laws of momentum, conservation of momentum, conservation of mass, and conservation of energy. The first equation that we are seeing is the continuity equation that works on laws of conservation of mass. Then laws of conservation of momentum, where your Newton's second law will be applied, and then laws of conservation of energy. Now see how complex it is looking, right? Let us just make it a little bit simple. See, when we say conservation of mass, you see, when we let us take a small example. When we suppose garden in our garden, when we give water to the plants, you observe when you press the mouth of the pipe, the water goes to a longer distance. Why is that happening? That is conservation of mass. What conservation of mass says is the amount of water that is going to enter into a system should be equal to the amount of water that is existing in the system. So when we actually compress that mass and velocity are always there. So suppose the mass is entering at a certain velocity in a larger mouth, and we are again compressing the mouth and the exit in the exit scenario, what happened is now the mass is not going to change because we are talking about conservation of mass. So what's going to change? The change will be in the velocity. So that's why you see the fluid is actually moving to a longer distance because the mass is getting conserved and the velocity is changing. Right. So that is what the first equation meant. Now the second one, the conservation of momentum. As I already told you, it depends on the Newton's second law, right? So what is Newton's second law? That is force equal to mass into acceleration, that we all know. So as I told you, when a fluid is moving, we are going to study about different forces that are acting on it, right? So when the fluid is moving, obviously the fluid has a mass, right? That's why it is called, and that's what we call here density. And it accelerates, right? So that acceleration is given by the change in velocity and the direction and the speed, everything. And the right hand side that you can see is the forces that are acting. Now, these forces can be of many types. One is the external force like gravity, or in our case that we say MSD or magnetic MSD or a magnetic effect, or you're giving some electric field. Those kind of forces will be your external forces. Then there is pressure gradient. Now, this pressure gradient might be present, might not be present, depends. And there are internal forces like viscosity, I've already told about, right? Viscosity is the internal resistance that the fluid is having. So these forces are all acting on the fluid. Now we have to study all these things, right? That will be your conservation of momentum or the momentum equation that we're talking about. And then there is a energy equations based on the same principle. So now after we know that what actually the Navier-Stokes equation is, I have tried to actually just take a small example of our research work. Now, suppose you see, let me say that the horizontal line is a seat, is a stretching seat or a stretching surface that is stretching in both the directions, right? And what I am going to do is I'm going to flow a fluid over it. Now, because the surface is stretching, the layer of fluid that is just attached to the surface, it is also going to get stretched in both the directions. And the layer just above that layer is also going to stretch, but it is going to stretch less. Then above that layer, again, it is going to be stretched less. So like that, if I go up, you will see there will be a layer formed like this within, just in close of the surface. So this layer is called as the boundary layer, right? And very interestingly, when the study on fluid dynamics started, nobody knew about this boundary layer. Everybody was taking the fluid and they were just trying to measure. It was actually plundered. We actually first discovered this boundary layer concept. That whatever nature it is showing at above surface, below that also there is a layer forming, and within that layer, lot of major impacts are going to happen, and that layer is called as the boundary layer. So we will be studying more about this in our field. We study more about this boundary layer because measure of the impact happens in this boundary layer in the below, in the adjacent to the surface. Right. So here what we have done is we have taken a surface. We have said there is a fluid flowing, and because the surface is stretching, the fluid is also getting stretched. So the layer just adjacent to the fluid surface, to your heated surface, and this surface is a heated surface that I talked about. Like suppose there is an industry and there is a surface there that is heated, and we need to cool it down. So and we are saying that when the surface is heating, it is also stretching alongside. So what we are doing is we are taking a fluid, basically a nanofluid for more efficiency. And that fluid is also getting stretched and that is creating a boundary layer. Now, I will not go into details about what is this boundary layer or not, but our general concept here is we want to cool down the surface, right? And this, see, if there was a normal fluid, suppose there was only water, water is going to absorb heat from the surface. That is true. But now, because we have also added these nanoparticles, the heat is going to get absorbed more because water will also absorb and these particles will also absorb. So our heat transfer will be more efficient. And that is what our objective here. Because we want to maintain the temperature. In present scenario, most of the cases, base fluids like water and oil, these are not actually efficient enough to cool down those surfaces because we're talking about very high temperatures right now. So by introducing these nanoparticles or more than one nanoparticles, we are actually increasing the efficiency of the fluid. So our study is mainly focusing on that how how my nanoparticles should be, what should I add, how it should behave, what should be the flow, like that. And our main objective is to transfer that heat from the surface to the fluid. And once the surface heat is transferred to the fluid, it might radiate it, you might radiate it outside. Or what you can do, you can just connect it to a heat exchanger where this heat will again be stored in the heat exchanger, and that heat you can again use for different purposes. So this is just a basic example model I've taken, right? I've just described a little bit about that, like the x-axis, what is x-axis, what is y-axis, and how the temperature. When we talk about the ambient temperature and the surface, when ambient temperature means, like I said, suppose the fluid is flowing, right? So the layer that is just connecting the surface, that is your surface temperature. But because when we go layer by layer above, that heat is going to get reduced, and there will be a certain point where the temperature of the fluid will be there, right? So that kind of fluid will be called as the free stream fluid or the ambient fluid temperature. And there are, I already told you that we are taking magnetic field because we are talking about smart fluids. So here we are considering a magnetic fluid, your magnetic field that is going to affect that fluid because we are taking nanoparticles. So those nanoparticles are actually going to be affected by this magnetic field, right? Now, basing on that Navier-Stokes equation that we have considered, we have tried to model our equation, our set of equations according to our requirements, using the basic fundamentals of Navier-Stokes equation. The first equation that you can see, that is your equation of continuity. The second equation that you can see is the equation of momentum. Now, if you actually, let me just give you a small hint here. The left-hand side that I talked about, that is mass into acceleration. The right-hand side is the force. Now, if you see, there is a term in the second equation that is sigma b0 square, right? That is your magnetic term. That means what? The magnetic force is also acting there. And then there is G. G means gravity. That means gravity is also acting. So what we are doing is we have taken a fluid along the surface and we are just testing that what are the different, if we give different forces, like gravity is already there. Suppose we also give magnetic field is there. Suppose we also give some other forces. How this is going to affect the fluid velocity, and that in turn will affect the rate of heat transfer that is going to happen, right? And the third one is the equation of energy. Energy means here mainly temperature, how temperature is behaving with the fluid velocity. And now the last thing is boundary condition. Now see, whenever we take Navier-Stokes equation, we can't actually directly solve it. That solution does not exist right now. We have to use certain boundary conditions, right? Within a certain boundary only we can actually measure what are the different effects. So that's why those boundary conditions are also very important. Now, these kinds of gives you a restriction because once you talk about boundary condition, not all numerical methods you can use to find the solution, right? There are different numerical methods that we use, like finite element method, finite volume method, or simpler like RK methods and all. We use those because they accept boundary conditions, but we can't use those methods that does not have boundary conditions, right? Now, once we know how to derive the problem, how to derive the problem basing on the Navier-Stokes equation, we mainly concentrate on these two physical quantities. One is your skin friction and one is your Nusselt number. Now, as I told you, the most important thing is we are considering is we want to reduce the heat in the surface. So the main thing is that heat transfer that is going to take place. So that heat transfer rate is called as Nusselt number. Now that Nusselt number, what we are going to do is we are going to measure the Nusselt number, and according to that measurement, we are going to do the analysis whether the heat transfer is efficient or not, right? And obviously, skin friction is the surface drag, but my main concentration is the Nusselt number here. These are certain graphs that I have shown here. Like here, the HA square is actually the magnetic parameter that we are using because we are using a magnetic field. There is a magnetic parameter there that we get after solution. So what happened is, you can see here, when we increase this magnetic parameter, or we, in general, I can say, if we increase the magnetic field, in this case, the temperature is increasing. And here the temperature means the temperature of the fluid. And the fluid velocity is decreasing. So what is happening is, you just understand it like this. Suppose I'm giving a magnetic field, right? The fluid is moving. Now, if the fluid velocity, now because this magnetic field kind of reduces the flow, that flow becomes slower. Now, that means what? At a particular heated surface, the fluid is spending more time because the velocity is slow. So, because it is spending more time, it is kind of absorbing more heat. And that's why the temperature is increasing. Now, it has its own merits and demerits. Sometimes it might be helpful, but sometimes it might not be helpful. Sometimes you had to increase the velocity, because once you increase the velocity, more fluid will be coming into a particular surface and more fluid will be going out. Because see, when we keep the fluid constant, suppose at a certain place, it's after a certain time it's going to reach its saturation. That means no more heat it can take. Right. So in that case, if we increase the velocity, more heat will be transferred. So depending on the situation that you require, we can actually model those things. So here I've just tried to show you how this model is kind of working. Similarly, I have taken different parameters here, like radiation parameter. Radiation means how much heat is radiating by the fluid. So if more heat is radiating, that means if more heat is going out of the fluid, that means more heat it is kind of taking from the surface. So that means more heat transfer is taking place, right? So those kind of analysis we are here doing, right? And then again, different parameters are also there, like Prandtl number is there, and your S means the Squimbit number is there, right? So now this is the basic fundamental of fluid dynamics, right? For my case, I'm saying for an industry surface, our main objective is we have to cool the surface, we have to maintain that temperature. And for that, we are using different kind of smart fluids. These smart fluids can be made using base fluid and mixing nanoparticles to them. And depending on the number of nanoparticles you are adding, it is called a nanofluid or a hybrid nanofluid or a ternary nanofluid. A lot of things are there. And once we make that fluid, we kind of take a flow above the surface, and we then try to control that temperature of the surface, right? Now, this was the basic model. This is a basic method that was happening till now. Now, once that AI came into the scenario, things got a little bit interesting. Now, what happened is, I told you that there is a number called as Nusselt number, right? That is the rate of heat transfer. Now, what happened is, I told you we have to measure that number. Now, when I take this model and I run in my computer, this is just a simple basic model, right? But in actually real world applications, the models are very much complex. So now I said, as I showed you in the graph, the magnetic parameter I'm increasing, right? Suppose 0.2, 0.5, 0.6, I'm trying to, so for 0.2, I have to run the model once. For 0.6, again I have to run. For 0.8, again I have to run. So, and that running computational cost is very high. And it's very time taking also. Means if you can, if I want to tell you, this simple, this simple model will take around maybe half an hour to 1 hour just to find one value. And you see how much time is required. And I'm talking about the simple application right now. So what AI can do is, once we get that values, suppose that Nusselt number value we are getting from 0 to 20 or 30, and the interval is 0.1. So 0, 0.1, 0.2, all values we are getting. So what we can do is we can train a model that can actually predict the value above a certain limit, right? So I suppose I want to know what is the value at 60. I don't need to again compute for 30, 31, 32 up to 60. I can actually try that predictive model. Now, it might not be accurate, I understand, but it kinds of helps you to give an idea, and it kinds of help us to reduce the computational cost. And this is just a basic example, right? And also, the second point that you can see, that is a real-time control. Actually, basing on this topic also, we have actually published a patent. And what we are doing is, we are taking 3, 4 different fluids, and we are, suppose I have taken a water, then water with some nanoparticles, then water with other 2 or more nanoparticles, then 3 or more nanoparticles, like that we have taken, and we are flowing it in a surface, right? So what, and we have introduced a device called as your AI simulator device. Now, what it is going to do is, it is going to read the temperature of the surface. So if suppose less temperature is there in the surface, so if water can do the tasks, why to waste nanofluid? Because once you use the nanofluid, it is going to get degraded. Right. It's so suppose temperature is less. If water can do the work, we'll use water. Suppose temperature becomes higher and water is unable to now control this temperature. Now I will use nanofluid. Then again hybrid, then ternary. So depending on that temperature, we can automatically, it will control the temperature of the surface temperature, right? So that was our idea then, and we have actually modeled that device also. And last is the predictive model that I have discussed, right? So what is the application? Application I've already told you, right? Adaptation of adaptive substances like suspensions, like I've showed you when the car is moving, right? If I could no, direct the fluid to the required surface, how smoothly it is going to move. Now that Direction is not always going to be done manually. So their AI is required according to the force that it is getting. It will direct the fluid to that particular surface or to that particular area where it is required. Right. And then I talked about target delivery and ferrofluids. Ferrofluids means that fluids that have iron particles basically. Then aerospace also, because whenever flight is going up, we are moving in air. So air is also a fluid. And like that. What are some challenges? Now see, as I told you, it takes a lot of time to compute, right? And I'm talking about theoretical comparison. When I go to practical, you need setups. And again, lot of resources you need. So there is a very big data scarcity in your smart fluid experiments. And because of this data scarcity, that accuracy of the model is not always, it is not always possible to achieve that, right? Then obviously, because now we are using physics and maths, again, you are going to put machine learning in there. That machine doesn't understand physics, right? We have to make it understand. So that particular integration also becomes very vital. Then validation, right? So validation means what? Suppose we get a value at, suppose I told you an example, we are getting a value at 60, but we don't know whether it is true or not. We are just, that depends on the accuracy of our model, right? So a lot of challenges are there. That's why it is a very growing area right now, and a lot of work has been continuously done in this. So these are some of the challenges, right? So today's talk, my main objective was to make everybody introduce what is the fluid dynamics, how we work in fluid dynamics, and because AI is emerging, if somebody is interested, they can actually come and join us, and we can actually work on implementing this AI in this fluid dynamics part. I wanted to give you a clear idea. And uh, even if in half an hour of time, it's very difficult to actually go deep into the concepts of how equations are made and how we are going to solve, right? So I just tried to give a general idea of how the fluids behave, how we study the fluids in general life, and how AI is going to get applied to this fluid dynamics. So, thank you.
Thank you, sir, for your presentation on topic smart fluids, how AI is reshaping fluid mechanics. In this regard, is there any queries from the participants? Okay, well, thank you very much.
Two feedbacks
Yes, sir.
from two of our members. Actually, it's a very based on their input. Also, we also enjoyed, very informative. It's a very short notice, but you again really made us more informative, sir. Thanks a lot for your wonderful session.
Thank you, sir. I just wanted to give a general idea about my field, and actually, it's a very evolving field right now. And we are welcoming everyone to come and join us. And
Oh,
and I also like to thank you for giving me this opportunity, to speak about it.
okay.
Yeah, thank
So
you,
may
sir.
I
Actually,
know which
initially I have
field?
a doubt. When I go through the topic, what is the current between AI and actually you are belongs to computer applications, then fluid. Actually, I have some actually confusing base idea, but wonderful, sir. Thanks a lot.
Uh, Actually, sir, my background is mathematics.
Oh,
Then
super.
Mathematics. Oh,
yeah, this fluid dynamics is actually my base course, my base.
because
Then
while we are saying,
I joined computer application. Now I studied then AI. Then I try to
oh,
combine those subjects.
Mm.
well, because from your biodata, we thought that you belongs to computer application, but
Yeah,
on
yes, sir.
hearing your presentation, I had a doubt that you are from mechanical engineering or either civil. So you are well versed in both civil and mechanical because you have qualified yourself in fluid dynamics and heat and mass transfer and all that. A really wonderful presentation, sir. It is really very useful,
Yes,
interesting,
sir.
and informative. Thank you very
One
much.
again member from mechanical, one member from civil. They again enjoyed your session and they gave again wonderful feedback about the session, sir.
Yeah,
Thank you.
yeah.
Thank you.
Right, sir. Then thank you very much. And I would like to invite the Honorary Secretary of IEI Salem Local Center to propose word of thanks. Please, ma'am.
Thank you, sir. Sir, I'm audible, sir?
Yes, ma'am. Yes.
Okay, thank you, sir. Most respected our chief guest and the keynote speaker, Dr. Satya S. Sen, sir. Respected our chairman, Dr. K. Thangaraj, sir. Respected committee members, state and local members, respected Arumugam, sir, and Thiagu, students from various organizations. Good evening to all. As we proudly celebrate this 30th anniversary of IEA, Salem Local Center, we are delighted to invite you for the 97th special webinar, our ongoing weekly online lecture series, Engineering Talk, in the topic Smart Fluids, how AI is reshaping the fluid. First, I would like to extend my deeper to our chief guest, Sensor, AP Applications, Kalinga Institute of Industrial Technology, Bhubaneswar, Odisha. Sir, thank you so much. As everyone told, it is very interesting topic. Even though you are a mathematic, belongs to mathematics, we understood a lot about the what is the fluid mechanics. You explained very well, sir. So for delivering, thank you for delivering such an insightful and thought-provoking session. Your expertise has given us a new perspective on how artificial intelligence is revolutionizing the fluid mechanics and shaping the future of engineering and research. Thank you so much, sir. We extend our deepest gratitude to our chairman, Dr. K. Thangaraj, sir, for his constant encouragement and support in organizing all the seminars in IEA. I extend my sincere thanks to our engineering talk team series for their continuous guidance and support. It's my privilege to thank Engineer N. Arumugam sir for always being with us and support in all the activities. Thank you so much, sir. I would like to appreciate Mr. Thiagu for the sincere effort taken for arranging all the seminar. Finally, we thank our one and all who directly, indirectly contributed to the session of this event. We hope the knowledge shared today will inspire further exploration and innovation in the fascinating field of the fluid mechanics and artificial intelligence. Thank you once again. Thank you, sir.
Thank you, sir. Thank you, ma'am.
Thank you, ma'am.
Thank you, sir. Thank you, sir.
Arun, sir, thank you.